So IVT and MVT on table. So most importantly, I'm going to be really going into a lot deeper on IVT and MVT. There will be a question about EVT in your homework. I think I kind of really covered that in terms of yesterday, a little bit more so. I'll just reiterate that as well. But these are referred to once again as the existence theorems of calculus, which are IVT, sorry, the intermediate value theorem, IVT, the mean value theorem, MVT, and of course the one that we already covered, the extreme value theorem, EVT. Each notes a property that must occur at least once within a given interval. So, so let's talk about IVT. Now, first off, there is a requirement for IVT, and it says that if f of x, and I know I'm repeating yesterday, and that's perfectly fine for us, if f of x is continuous on the closed interval a to b, now this part right here, this is the requirement, or the requisite. So that must be true for IVT. The function has to be continuous on a closed interval. Then there must exist a value f of c for a less than or equal to c less than or equal to b such that f of c is between f of a and f of b at least once. So, in layman's terms or in the visual field, and I showed you this yesterday. If we have f of a, and here's a, here's b, visually it's the same for every value c that's inside here, and here's f of b, and I have the point here, and I have the point here. Basically, no matter how you draw this graph, and they have to connect since the function is continuous, every value f of c, all of these values have to happen at least once. Every value inside here, every value within that interval must happen at least once. And I know that's kind of like, I'm looking at my image right now, and it's kind of like a little bit on the high side right there. Every single value, no matter what the value is for the output. So this one looks at the outputs and says, hey, the output of the function, any value between f of a and f of b must have occurred at least once. Now, traditionally, typically use for showing change of sign as a proof for a given function. So typically it's there, unless a value for f of c specifically stated. And so every single value between f of a and f of b must be taken at least once. Now, let's look at an example of this. And of course, today we're focusing on tables. So I'll give you more of like a word application values over tomorrow. So you're given a value, and the tables can go up and down or left and right. So this table is going to go left and right. So we got x, we have f of x, and then, so we have like 0, oh, sorry. Like 1, 5, -6. Well, what am I doing? 1, 3, 5, 6. And then I have for my outputs -5, 3, 4, -8. And the question would be something like, show that and actually I'm going to change it even one more. Let's say these are the derivative values. So this is x and f prime of x. These are the f prime of x. Show that f prime of x, or actually I don't want to say show. What is the minimum possible horizontal tangents for f of x. Justify. Now, this problem right here is talking about a horizontal tangent for f of x. If there's a horizontal tangent for f of x, we need to translate that into calculus. And what does horizontal tangents for f of x mean in calculus talk? So translate algebra, translate pre-calculus horizontal tangent for f of x into calculus into calculus. What does that mean? What do we mean by that? Somebody. The writing's on the wall. I've kind of hinted at it in the last couple of minutes. When you see horizontal tangent for f, you must think what? You have to decode this. This is the biggest part in terms of passing the AP exam. If you don't know what to do, you can't do it. So everything that I can teach you, the problem's not going to say use IVT. The problem's not going to always tell you exactly the information. So what does it mean by a horizontal tangent for f of x? It has to be able to click. Visually, that's what goes on in your mind. What does that mean? Close. Very close in the chat. Means, yes, f prime of x equals 0. So sometimes, and I think in your homework tonight, it's going to explicitly say like f prime of x equal to 0, or the function equal to 0, or the function changing signs even. How many extremas could there be? Could there be? Now this is the minimum number. This is possible. The minimum times possible. Now, if we look at this and we read this, we can see that, and you can go into a lot of greater detail, but f of negative, so this graph on the interval 1 to 3, the function goes from -5 to 3, and on the interval 5 to 6, it changes from 4 to -8 in terms of f. All right, so what is the answer? What is the minimum number of times that f prime, that the derivative, this function value, that derivative of what we're looking at, what's the minimum, and it's kind of obvious in terms of, but what's the minimum number of times it must change sign? What's the minimum number of times it must, f prime must be 0? We're looking at the outputs. The output goes from -5 to 3. What had to happen? 3 to 4, nothing special is going to happen there. And then goes from 4 to -8. What must have happened there? We need to get more responses though, class. We really need to get more responses. Even wrong, if you want to direct chat to me, that's fine. At least I know what you're thinking. So right here, and in the premise of what we're going to be doing tomorrow is that by IVT, f prime of x must equal 0 at least once, between 1 and 3, since f of 1 is less than 0 and f of 3 is greater than 0. So by IVT, we're going from a negative to a positive on that interval. So somewhere along the interval, f prime had to be equal to 0. Also, f prime of x would equal to 0 between 5 and 6, since f of 5 is greater than 0 and f of 6 is less than 0. So somewhere along the interval between 1 and 3, we don't know where, and this is the whole premise of IVT, somewhere on that interval, I don't know where it happens, but somewhere on the interval between 1 and 3, the graph that we're looking at, f prime, has to equal 0. Because the graph, the function values are going from a negative to a positive. You know, you don't want to spend the time, but the idea here on the values is going from -5 to 3 to 4 down to -8. So I don't know where. Yeah, this has nothing to do with the slope on this one. IVT is just outputs. Somewhere along this interval, 1 to 3, and somewhere along the interval 5 to 6, somewhere, I don't know where, somewhere here, you're going to have to cross the x-axis to get from the bottom to the top, and somewhere on this interval, you're going to have to go from here. Now, between 3 and 5, it could. There's nothing that tells me that the graph doesn't do this. There's nothing that says that it didn't do that, but I can't prove that. IVT tells me that at least one time, at least once, now it could happen more than once, but at least once it can happen. And so the answer is twice, or 2 horizontal tangents at minimum, or at least. And notice that I specifically, and the justification here is literally the IVT. Yes. So it's by IVT. All right, we're just looking at those values. Now, it could be for function values, f of x. Now, if I gave you a table, and so here's another example table, x, f of x, and this is f of x, all right? And I get 1, 3, 5, and 6, and I get like 3, 5, 6, 2, and then I ask you the same thing, at least how many times does f prime of x equals 0? I'm not going to relate to the example. So now, in this problem, I am given f of x and asked about f prime of x. IVT is no help. Okay, so this is basically the same question that I asked you before, but in this instance, I have not given you f prime values. So if I give you that function and I ask you about the function, that's IVT. Doesn't matter if that function is the function f or the function f prime. If I ask you about a function and I give you the values for that function, that's IVT. This is an instance where that does not happen. I've given you the values of f and I'm asking you about f prime. So IVT does not help, and this is where we get into, and we're going to come back to this table right here in our example, and we need to utilize and understand MVT. So MVT is used to prove slope values that must occur. All right. So MVT. So the mean value theorem says it's about slope. So that if a function is differentiable on the open interval a to b and continuous on the closed interval a to b, and once again this is a requirement and differentiability is a requirement for MVT, then there must exist at least once a point where f prime of c is equal to f of b minus f of a over b minus a for a less than or equal to c less than or equal to b. In layman's terms, the average rate of change must equal an instantaneous rate of change at least once. Okay? Now, visually, here's what it means. I have the value A, I have the value B, I have f of A, I have f of B. Now, if I connect these 2 points, the slope of the secant is what we call it. So also, this is another way of saying that the slope of the secant will equal the slope of a tangent. I'm going to actually reverse that. Will equal the slope of the secant. All right. So if I were to graph and I connect the points directly, that's the average rate of change right there. And of course, that's equal to f of b minus f of a all over b minus a. Now, it doesn't matter how I graph it. It doesn't matter how I connect these 2 points. It goes up, it goes down, it goes up. It doesn't matter. I just connected these 2 points. Let's say that's what the function looks like. Oh, I would select this part. So that slope right there, there must be somewhere along the graph where the slope that I got from connecting the two lines it must happen somewhere at least once. Now in this picture, I do want to note that in this picture, in this image, it actually happens twice. All right, it also happens down here as well. But MVT does not tell me how many times it happens. It just tells me that it happens once. No matter how you draw it, if you connect 2 points, then somewhere along those lines, or everywhere, because maybe if we're actually dealing with a line, then it happens everywhere. But somewhere along the graph, the tangent slope will be equal. In other words, there will be like a parallel lines type of thing, that if you took the tangent, it'll be parallel to the secant. The secant is the average rate of change. Somewhere, at least once, it will occur and will be that value. Now, NVT is typically used to prove a specific slope. We have what is known as Rolle's theorem, which is a proof of f prime of x equaling 0. So with Rolle's theorem, basically Rolle's theorem says that, and I'm not gonna reference Rolle's theorem specifically, but it says that if f of a equals f of b, then f of a minus f of b over b minus a equals 0. Then the slope f prime of c is equal to 0. Now, in an example, and we're not doing the example from the previous one yet, if I gave you a table value and I gave you x and I gave you f of x and I gave you 3, 5, 6 as the x values, and then I had like 2, 4, 2, all right. The idea here with Rolle's theorem is that you can specifically note that the slope is going to equal to 0 right here, because if we notice the two outputs between the interval 3 to 5, f of 3 is 2, f of 6 is 2, so f of 6 minus f of 3 over 6 minus 3 is going to equal 0, because it's going to be 2 minus 0 on top. And so by MVT, f prime of x must equal 0 once on interval 3 to 5. Because since the average slope was 0, the instantaneous slope must also equal 0 somewhere along that interval. And now notice in this instance, I had to skip. All right, I skipped because in order to get there, I went. Now, we also did something very similar to this one right now, beforehand. We can also use MVT and IVT to show the same. And here's what I mean by that. On the interval 3 to 5, right, the slope is greater than 0. And on the interval 5 to 6, the slope is less than 0. Now I can actually calculate the exact slopes if I wanted to. I think the slope is actually equal to 1. And over here, the slope is equal to -2 more specifically. So the actual slopes are 1 and -2. So if the slopes equal 1 and -2, what that tells me is that by NVT, f prime is going to equal to 1 on the interval 3 to 5, and f prime is going to equal to -2 on the interval 5 to 6. So now we have slope values. I know the slope value from 3 to 5 and the slope value from 5 to 6. Therefore, by IVT, f prime must equal 0 on the interval 3 to 6. Since f of 3, since the slopes from positive to negative. Now, that's kind of like the weird one that's going to be the most tricky one. So basically, here's what we said. We looked at the outputs of this table, and we just looked at the slopes. I noticed that the slope went from 1, the average slope on the interval 3 to 5 is 1. And so this is the whole calculus understanding here. The average slope, that's the slope of the secant, is 1. So somewhere on the interval 3 to 5, I don't know where, it could be 3.2, it could be 4, I don't know where between 3 to 5, but somewhere on the interval 3 to 5, the tangent slope, f prime, must equal 1. Somewhere on that interval 3 to 5. Somewhere on the interval 5 to 6, the tangent slope, f prime, must equal -2, since that's the average rate of change. Somewhere, I don't know where, it could be 5.2, 5.3, 5.44444, I don't know where exactly, but somewhere on that interval from 5 to 6, the slope is -2. So somewhere it's 1, the f prime is 1, somewhere f prime is -2, and therefore at some point by IVT, f prime had to equal 0. Let's look back to this table that I gave you up here. For our last example. Okay. So, question A is the more typical question. Show that f prime of x is equal to three-fourths on the interval for 1 less than x less than 6. Now, this one's an interesting problem. Now, why, somewhere along the point, the slope must be 3/4. Now, this is different than the zeros. So this one is technically an idea of checking every possible slope. And actually, I'm going to change this a little bit out because usually it doesn't do this. It usually says like 5. So we could check all possible mini slopes. In other words, I can find a slope right here. I can call that M1. I can find this slope right here, M2. But I can also find a slope from here to here, and I'll call that the third slope. Now notice that even though this table goes to 6, I'm saying only go up to 5. Typically, we don't want to make the problems too many slopes, but these are all the possible slopes. I can find a slope from 1 to 3. I can find a slope from 3 to 5. I can also find a slope directly from 1 to 5. And typically on these questions, the interval they give you is the one that they want you to use because they want you to be kind of quick with it. So if, for example, if I was trying to do this really sluggishly, I can find the slope from 1 to 3. M is equal to 5 minus 3 M1 over 3 minus 1, which is 2 over 2, which is 1. So somewhere between 1 and 3, the slope has to equal 1. F prime has to equal 1. Well, if I asked you F prime equals 1, that would have worked. From 3 to 5, I get M2, which is equal to 6 minus 5 over 5 minus 3, which is 1 over 2. So if I had said, prove to me that the slope was 1/2 somewhere on the interval, that's what it would have been. And if I look on this interval from 1 to 5, which again is what they gave me, that slope would be 6 minus 3 over 5 minus 1, which is 3 over 4. So by MVT, F prime of x must equal 3/4 at least once on the interval 1 to 5. And actually, 4 on for 1 less than x less than 5. Now, I'll kind of go over this into tomorrow's work, but sometimes a table will give values of f and f prime, and then they ask you about utilizing the same type of questions, and it becomes a little bit trickier because typically, and I just want to note this, on the AP exam, if table gives values for both f and f prime, but then ask about f prime, NVT should be used over IVT. So what happens is that I get a lot of students who, when they see this type of problem, they're like, oh, well, if they give me the values of f prime, I can look at the value of f prime and answer it. Now, typically on the AP exam, now that is true, but typically that won't give you the answer. They create a table such that if you try to use IVT on a derivative, because they also gave you the two values, then it doesn't work. So typically on the AP exam, when they ask you about f prime, you're using MVT. When they ask you about the function, that's IVT. You'll see in a little bit more practice. I talked to you about the extreme value theorem, about being careful about if there must be an extrema or not. Remember the extreme value theorem? We've covered it quite extensively, I would say, at this point, the last 2 lectures. I think you should be good on those with the delta math.